Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. Today, we are joined by Andrew Trask, PhD student at the University of Oxford and leader of the OpenMined Project. OpenMined is an open source community focused on researching, developing, and promoting tools for secure, privacy-preserving, value-aligned artificial intelligence. Andrew and I caught up back at NeurIPS to dig into why OpenMined is important and to explore some of the basic research and technologies supporting private decentralized data science. We touch on ideas such as differential privacy, secure multi-party computation, and how these come into play in, for example, federated learning. Before we jump in, I'd like to join Pegasystems, this episode's sponsor, in inviting you to meet me at the MGM Grand in Las Vegas from June 2nd to 5th at PegaWorld, the company's annual digital transformation conference. Pegasystems puts AI at the center of its customer engagement software so that every customer touchpoint on every channel is optimized in real time, so that customers find each interaction relevant and timely, whether a sales call, a marketing campaign, or a customer service chat. At PegaWorld, you'll hear great stories of AI applied to the customer experience at real Pega customers. The event is a great way to learn from a who's who of the Fortune 500, and of course, I'll be there speaking as well. To register, visit pegaworld.com and use the promo code TWiML19 when you sign up for $200 off. Again, that's TWiML19. It's as easy as that. Hope to see you there. And now, on to the show. All right, everyone, I am here in Montreal at the NeurIPS conference, and I am with Andrew Trask. Andrew is a PhD student at Oxford, as well as leader of the open source OpenMined project. Andrew, welcome to This Week in Machine Learning and AI.
Awesome, thank you. Great to be here.
Awesome. Why don't we get started by having you tell us a little bit about your background? How'd you get involved in machine learning and privacy and the intersection of those two?
Yeah, so I went to undergrad at a liberal arts college in Tennessee called Belmont University, and while I was there, I was originally a music student, and I stumbled into a CS course, dabbled around, and there was an AI course, and that got me really into machine learning. So as soon as there's this really great professor named Dr. Hooper, has many great stories. A really compelling professor teaching really exciting concepts. And I trained my first neural nets and got them to converge and got a paper into an undergraduate conference. And at that point, I was pretty committed on the machine learning front. After that, I joined a local company called Digital Reasoning that does deep learning and AI at scale on private data sets.
We're in Nashville, actually, right?
Yeah, they're in Nashville. Yeah. So Belmont's also in Nashville.
Okay. Oh, okay. Got it.
Yeah. And that's when I really got exposed to the power of doing machine learning on data that you don't have access to. So I mean, they work with a
lot of government agencies.
Three-letter agencies. Yeah. The intelligence community. Pretty. Oh, that's awesome. All throughout that story, I got to dabble in research as well as product management there, and really just came to appreciate how challenging it is to do machine learning and deep learning on unseen data. So when I left to do a PhD, I had already a very good appreciation for that, and also some sort of high-level understanding of the challenges of that environment. And then during my first year at Oxford, the first year of PhD is often very sort of exploratory. And one of the first things I came across was homomorphic encryption, which just to me was absolutely magical. I couldn't believe that you could do computation on encrypted data. And I wrote a blog post sort of just trying to jerry-rig some homomorphic encryption code that I found with training a neural net. And I got a tremendous amount of positive feedback from it. Ended up chatting with some folks at the Future of Humanity Institute in Oxford. So I don't know if you know Nick Bostrom and kind of the AI safety work that they do. And it just became really clear that there was a really exciting research opportunity here that one was underserved, so there weren't many people working on it. And secondarily, and perhaps more importantly, that there was good reason to believe that we can make a lot of progress in a relatively short period of time on a topic with pretty significant social gains. And so that at the beginning of a PhD is a no-brainer. Like you absolutely want to jump on those kind of opportunities. And since then, what I've discovered is that tons of great work has gone on in sort of the field of cryptography. Tons of great work has gone on in the field of statistics, and of course in machine learning and deep learning. But these three communities, they don't necessarily talk as much as they should. And so by simply trying to become as familiar as fast as possible with sort of the core primitives of these three different fields, and by just trying to combine them in ways that solve important use cases, I think we've already been able to make quite a bit of progress and expect to do so in the future. So that's kind of where I'm at.
Nice. Are there some kind of core concepts, maybe from the cryptography side, that it makes sense to kind of talk about? Like you mentioned homomorphic encryption, that are fundamental to all the rest of the stuff you're doing, or is it better to go top down?
So I mean, the three core concepts that we deal with, two of which are from cryptography, are differential privacy and secure multi-party computation. So, and then there's federated learning from the machine learning side.
Okay.
So those three things kind of make up what I think is the future of privacy-preserving machine learning. So differential privacy is concerned with, I suppose your viewers already know this, in the context of machine learning, differential privacy is focused on allowing models to sort of learn from a training data set without them accidentally learning information we don't want them to learn, like private
training
information
data itself, for example.
Exactly. Yeah, exactly. Or it's any specific features about a specific person, right? So it might, a good example might be, you want a model to learn to identify cancer in radiology scans without it memorizing which individual person has cancer, right? Differential privacy is super important. That one is already, there's already good community forming between that and the machine learning community. It's really exciting to see that develop. Homomorphic encryption and secure multi-party computation are a little less known. In particular, secure multi-party computation. Well, I'll say secure MPC from now on for short, because it's such a wordy thing. Homomorphic encryption, I think, is more intuitive for people because it's typically laid out in the form of a standard encryption. So you'll have a public key and a private key, and you'll use the private key to encrypt something, right? So I can encrypt the number 5, and then I can give it to you. And while it's in its encrypted state, while you have it and I can't see it, you can do arithmetic with that number, right? And you could do computation with that number. And then you can give the result back to me, still encrypted, and I can decrypt the result. And so that's interesting from a machine learning standpoint because I can take, say, all the parameters of my model. So a model, a neural net, for example, is just a big collection of numbers. I can encrypt all of them. I can give them to you, and then you can do prediction or training or anything else that you'd like to do with a machine learning model. So if you do training, for example, you can give me back the resulting model, and you were able to. It's sort of a one-way information flow where you're able to make the model smarter, but you're not actually able to use it. So there's lots of interesting commercial use cases that protect privacy in that context. The one, and some people have heard about this. So homomorphic encryption is sort of mildly well known, but the problem is that it's very, very slow. So I mean, it's several, meaning more than 5 orders of magnitude slower than typical what we call plain text computation, what we do normally.
Okay.
And this is where MPC really starts to become interesting. So there's secure MPC is a slightly different setup. Instead of trying to encrypt a number, we actually split it into what's called shares. So let's say we wanted to encrypt the number 5. I can take the number 5, I can split it into 2 shares, we'll say a 2 and a 3. Right? And I can give you the 3 and I can hang on to the 2. So the 3 is your share, the 2 is my share. And now we could restore this number 5 by just adding these 2 shares together, if that makes sense. But the interesting thing about secure MPC is that while it's in this state, neither of us know what the number is that's hidden between us, right? So you may have no idea that this was a 5, but we can compute over it. So let's say we wanted to multiply it times 2. Like if you multiply your share times 2, I multiply my share times 2, then this hidden value that's between us was also multiplied by 2. This is better than homomorphic encryption for 2 reasons. One, it's much faster typically. So there's a recent paper showing you could train a deep convnet that's only 20 times slower than normal, which I know that sounds mildly annoying to anyone who's training deep neural nets, but it's totally different than like 10,000 or 100,000 times slower, right?
Is it faster only in aggregate or for each individual participant?
So it is. In this specific setup, it's 2 or 3 party computation. So we've split this deep neural net, all the parameters in it, into shares that 3 parties own. And it's in that case, it's faster in aggregate. So we typically try to measure it in the context of a use case because different functions. So you can imagine this is a protocol, right? And I described how to multiply this hidden value 5 by 2, but addition is different from multiplication, which is different from comparison operators, which is different than how you bootstrap sine and ReLU and like sigmoid and all these kinds of things. So we typically try to look at the end use case and just sort of give high level empirical results for what the slowdown is. But the interesting thing is,
one more on that. If it's based on homomorphic encryption, how does it end up being faster than homomorphic encryption?
So it's not always based on homomorphic encryption. Sometimes there's a homomorphic encryption component. They kind of steal ideas from each other. But the cool thing is that since it's not a form of encryption, it's a protocol for sharing.
So encryption is not necessarily involved. It's more.
Yeah, so it's funny because it has an API that's very similar to encryption to the extent that I can take a value and I can make it so that a group of people can't see it, right? But we can still compute over it. So to that extent, it can do everything that homomorphic encryption can do, but it has 2 specific properties that are different. So 3. One, it's a lot faster because you're exchanging heavy compute typically, which is homomorphic encryption, for more network overhead. So whereas with homomorphic encryption, I could just send you an encrypted asset and you can do things with it. With MPC, we have to be online the whole time. It's a protocol for how we can exchange messages in a way to compute functions on hidden data. And there's 2 properties that we really like. One, it gets this privacy property, but secondarily, and this is different from homomorphic encryption, everyone has a private key. And this it's a lot more like shared ownership of a data structure instead of just encryption. So in this particular case, if I take a neural net, I take all of its parameters and I split each parameter into 4 shares, then I have 4 governors. I have 4 owners for this model, and any one of those 4 people could say, "Oh, I'm not willing to perform computation with you guys on this data point because I haven't been paid, or because I don't believe in it, or for whatever reason, right?" And that's fundamentally different from homomorphic encryption, which kind of defaults to a single owner who has a single private key. We really like that sort of distributed governance apparatus.
It's kind of nice. And so where does OpenMind come in?
Yeah, so OpenMind is basically about lowering the barrier to entry to being able to use these tools. So as I described a minute ago, these communities have kind of lived in separate worlds. So the crypto community has their own toolkits, typically in C++. The machine learning community has their own toolkits that's like PyTorch and TensorFlow. And statistics has their own, which is like R and all these kinds of things. So the problem is that if I want to do deep learning with Secure MPC, I either have to take an MPC framework and write all my autograd and my layer types and all that stuff from scratch, or I have to go to a deep learning framework and know all the cryptography to be able to add. And as it turns out, this is prohibitively difficult. And nearly most papers that I come across, people write some big amorphous C++ blob from scratch. And then it becomes difficult to repurpose, difficult for industry to pick up. So what OpenMind is all about is about installing these cryptography primitives inside of the major deep learning toolkits, so PyTorch and TensorFlow being the first 2, so that people in the machine learning community don't have to really know anything about cryptography to be able to use them, right? Or be able to do research on them, to be able to study these different protocols. So in particular, in one example of that is in PyTorch, we have this new tensor type that's an MPC shared tensor, right? So it feels like a normal tensor, has the same API, but every time you add 2 tensors together, under the hood, it actually sends messages to multiple different machines and does the protocol correctly.
Is the multi-party aspect of it, is it like widely distributed? Like you might think of, the parties representing actual people that are in different corners of the earth, or is it, are the parties typically like computational processes that might be local, to an environment and under the same control? Like how does it typically, what's the typical topology?
Great question. So for the purpose of development, we've got nice sort of what we call virtual workers that will simulate it on one machine so that you can build protocols and that kind of thing. But in the context of a more real world use case, there's different philosophies on how it will actually roll out. So the thing to know is that the more people you have governing a data point, the more people have to touch it for it to be decrypted or for it to be used in computation. So meaning the more owners it has, the slower the computation is going to go. So our vision is that most of sort of privacy preserving machine learning will operate with 2 owners at a time, because that's sort of the fastest version of it. And this is where, as I think I may have mentioned this before, we really see a trifecta of like 3 core technologies coming together, Secure Multi-Party Computation being one of them, and then Federated Learning and Differential Privacy being the other. So the nice thing about Federated Learning is it's a protocol that allows me as a model owner to train a model on a highly distributed data set by performing training with one person at a time, right? So I'll send a model to someone and it will train there for a while. I could do this like with 10 people in parallel.
Okay.
But the nice thing is that, actually, I should probably come back to that. So the short answer is I see it happening 2 people at a time.
Okay.
And when you combine it with these other technologies, that actually works out to be quite performant.
When do you want to go back to the federated?
Oh yeah. So
it's an interesting topic.
Yeah.
How well developed is that in the literature, the models for federated machine learning? I've seen a lot of work on distributed training. And then more recently in the context of like IoT and like edge devices, federated training in that sense, where you are trying to do some amount of learning kind of at the edge, but also share the model back to some centralized thing so that it could incorporate learning from other edge devices, but also so that it becomes like the master model, and then you ship out updates back out to the other edge devices. I don't know if the same kinds of techniques apply or what the overlap might be there.
They absolutely do. So I think federated learning is, out of these 3 things, like federated learning, multi-party computation, and differential privacy, federated learning is the most mature. I mean, to that extent, so if you have a smartphone and you open it up and you go to text someone, you know how it tries to recommend the next word for your text, that model for both, to my knowledge, to both Apple and Google, is trained using federated learning. So to that extent, federated learning is already deployed on billions of devices around the planet. So to that extent, it's quite robust. And the nice thing about federated learning, so I guess for anyone listening that doesn't know what federated learning is, typically when you're training a machine learning model, you would aggregate all of the data to sort of one central server. Then you'd initialize a random model, and then you'd train it on that data, right? So federated learning kind of flips the script and says, instead of bringing all the data to the model in one location, you're going to bring the model out to the data wherever it already lives. And the general goal is that whoever owns the data doesn't want to have to send it to someone. They want to own and maintain the only copy. So in this particular case, this means that if I've got a billion phones, I as a central server will then send the model with some instructions on how to train it down to individual data owners. And this is where the nice thing about that is it does 2 things. 1, it protects the privacy of the data, and 2, it typically actually results in less communication than sending the data to the cloud. So if you look at the original paper on federated learning from Brendan McMahon, I think they cited 10 to 100x less network overhead than sending the data sets to the cloud. I mean, it depends on how big the data set is, but often it can actually be less network intensive. And so as you can imagine, this is where MPC comes in. So the nice thing here is you protect the privacy of the data, but the problem is that you send a plain text copy of the model to potentially thousands or millions of people, right? So if this is your $10 million healthcare model, well then you're sort of at risk of any one of these millions of people stealing it and trying to monetize it for themselves.
Right.
This is where secure MPC becomes interesting. So instead of sending the model, you would MPC share the model, and they would MPC share their data set, and I would perform sort of encrypted training with each individual person in parallel, and then only aggregate their gradients sort of at the end. This is why sort of federated learning allows you to do MPC sort of 2 people at a time, which is quite a bit more optimal.
What's the kind of user experience of OpenMind? Is it like system level package that they're using, or is it more framework level? Is the typical user a developer or a data scientist? How do you kind of look at the world from that perspective?
Yeah, so speaking from today, it's mostly at the framework level. So our target audience today is primarily sort of machine learning researchers, data scientists, perhaps working at enterprise wanting to do a pilot in privacy preserving machine learning. So the vast majority of the code that we've written is extending PyTorch and TensorFlow. So if you're not a PyTorch or TensorFlow user, or you don't have any, then we're not quite ready for you yet. I think in the future, this will likely get packaged more into sort of, here's your federated learning system. Like, here's how you spin up the server, and this is where all your data adapters will attach and that kind of thing. But we still have quite a bit of code to write until we get there.
And so is it extending your PyTorch and your TensorFlow in an analogous way to the way different distributed training methods are working?
Yeah. Yes. So for PyTorch, for example, the first thing we built was a remote execution protocol. So for anyone who knows PyTorch that's listening, it allows you to take a tensor, which is just a simple list of numbers or nested list of numbers. So if we have a tensor called like x equals, some tensor, maybe 5 zeros or something like that, I can go x.send and send it to some machine. I put in the address for that machine. Okay. And then what gets returned to me is a pointer to that tensor. And then whatever that pointer has the exact same API as a tensor normally would. So it feels like a normal tensor. Okay. But the nice thing is that then we can use this underlying primitive to coordinate remote executions and to coordinate higher level protocols like Secure MPC. So most of it's built on top of that kind of a remote execution paradigm. But then the API...
And that was standard already existing in both PyTorch and TensorFlow, something analogous to it?
So PyTorch and TensorFlow have not had pointers in the past, so that's a new thing for us. Okay. But the thing that we try to keep the same is we want that pointer to basically have the exact same API as if the data was on your local machine, right? Okay. Because the idea being that we want to make it so that you don't have to relearn a new framework or really any other paradigms to be able to use things like federated learning or MPC. And that's why our MPC tensor feels like it's a normal tensor. Like it feels like it's on your device, has the same API and protocol, and you can do the same things. You can call back propagate on a lot of like on the remote tensors. But it's under the hood, it's actually doing all the protocol for you, such that you don't have to learn that protocol yourself. Okay.
And when you're using this API or to get the pointers, you're specifying the number of parties and like IP addresses or something like that, or?
Yeah, so we do have the ability to spin up servers, which we call workers, that are connected via sockets or web sockets. And what you'll get is actually a pointer to that worker on the client side. So we typically name them Bob and Alice canonically, just because that's sort of the
crypto literature.
Yeah, exactly. Yeah. So we have a big set of tutorials. Actually, we just listed that shows how the whole protocol goes. So if you go to our GitHub /examples/ so the PySIF library is the library that I'm referring to. The PySIF /examples/ tutorials will have that. But so if I'm going to send it, I'll go x, my variable, .send, and then in parentheses I can put in one or more workers that I want to send it to and return a pointer to that. For MPC, I go x.share, and then I pass in a list of pointers to their workers that I want to MPC share it to. Yeah. And that's the sort of the encrypted version.
Do you also have kind of flexibility over whether you want to use encryption or just MPC, or whether you want to layer in differential privacy, or is the framework making those kinds of decisions for me?
No, so the framework is totally agnostic to those decisions. So obviously we have higher level libraries that try to give you nice defaults, but the bulk of the framework is this low level protocol for allowing you to either design your own sort of remote execution strategies or to pull one of the off-the-shelf ones that we provide, like federated averaging or different kinds of MPC protocols. I think we have 2 different MPC protocols.
Okay. And what are the distinctions between the different protocols?
So they're APIs primarily. So the first one we implemented was called Speeds. So Speeds is a protocol that allows you to do, in our case, addition and multiplication. And then we extended it with this new protocol called Secure NN, which allows you to do comparison operators. So to compare 2 encrypted numbers. And then as it turns out, we can bootstrap sort of the rest of the deep learning API just from those 3 core primitives.
How mature would you say is the particular the project and kind of the ecosystem around it? Like, are you finding folks extra? Is it like your personal effort mostly that's kind of pushing along, or are there other folks that are kind of jumping in and contributing? How's that been going?
So that part's actually been going really well. So I think OpenMind Slack team at this point has around 3,400 people in it.
Wow.
Yeah.
Oh, wow.
And I think we're up to 170 or 180 people who have contributed code.
Oh, wow.
So to that extent, like, I think a lot of people get that privacy is important, that these tools are a really compelling answer, or they could be in the long run, and that by building better research tools and bringing these two kind of crypto and machine learning community together, that we can make a lot of progress. And then it's worth their nights and weekends to work on.
Uh-huh.
That being said, I would describe PySift today as kind of an alpha level project. So PySift, again, is the extension to PyTorch and TensorFlow. OpenMind is just kind of the general community name.
Okay.
So yeah, PySift is kind of in an alpha phase where it's got all the features that we would like for it to have, but they're not necessarily at like a product ready state. And they're also using an older version. In the particular case of PyTorch, they're using 0.3.1. So the main push at the moment is to upgrade to PyTorch 1.0, which was recently released, as well as to really make them robust enough that institutions can do kind of pilots and practice use cases and these kinds of things. And we're hoping to release that around February, March.
And are there any examples of use cases that you can talk about?
So we are in the midst of crafting several early pilots, but I don't think they're quite public yet, but okay. I'm very excited about them. We also do have several, I think about a half dozen firms that are in the process of putting together research grants for people to work on PySift and OpenMind full time, which will greatly help both their internal adoption as well as the health of the library, which I'm excited about.
Mm-hmm. And so where do you see this going? What are some of the next steps for the community and your research in general?
For my personal research, I think I want to sort of stay focused on whatever is needed for this stuff to become mainstream and widely adopted. Mm-hmm. At the moment, that's raising awareness and lowering the barrier to entry for tools that already exist, mm-hmm. and conducting research to solve sort of the holes that still miss in the technologies. Like there are some sub-problems, especially in differential privacy, that have not yet been solved to the extent that the widest use cases could be implemented today. So in the next kind of 3 to 6 months, I think that it's still mostly a research and open source tool push. In about a 6 month to 18 month timeline, I think that we're going to start seeing considerable enterprise adoption. So there's already some interesting movement happening in Europe as kind of an echo to GDPR. There's a handful of startups in the US that I've seen kind of growing up in this space. And so I think in probably the 6 to 18 months timeline is when enterprises which already have the data will be interested in moving into this space. You mentioned some kind of point challenges on the differential privacy side that need to be solved to better facilitate all of this. Are there some examples of those that you can share? So from what I've observed, there's two different kinds of differential privacy, right? There's local and there's global. Mm-hmm. Local differential privacy focuses on actually adding noise to each individual row of data to make sure that each individual row of data is protected before you even do anything to it, right? Mm-hmm. But as you can imagine, if you have 1 million data points, that means you're adding, a ton of noise to the data set as a whole. And you need to have like a lot of people in order to be able to get interesting insights about it because you've had to add so much noise to each individual data point. Global differential privacy allows you to compute some function on the data and then only add noise to the output, which can actually be relatively small amounts depending on what that function is. Mm-hmm. So one thing I have yet to see in deep learning literature is a global differential privacy technique that really fits the business use case that people want to use it for. The best one that I know of that comes to mind is the Pate algorithm, which I think if people know differential privacy and deep learning is probably the one that they'd be most familiar with. This is a really innovative approach wherein you split a data set into 10 different buckets, or in different buckets. I'll just use 10 as an example. Mm-hmm. And you train a model on each different one that's a private model. And then there's this clever trick where you can use these models to annotate a second data set that is a public data set in a way that all of the labels, you can sort of enforce differential privacy by the way that you label this second data set using these private models, such that you then train another model on this sort of synthetically labeled data set. Mm-hmm.
I think that one's Nicholas Paperno.
Yeah, that's right.
We did podcast interview with him as well.
Oh, excellent. Yeah. So I think that's probably the most famous and most successful general purpose deep learning for differential privacy algorithm that we have. But the problem is that it requires this second data set that you already have. And in practice, in industry, this is not usually the case, right? So if I'm a hospital network and I've got, say, 50,000 examples that are unlabeled, the friction for me to go to 10 other hospitals and train models with all of them and synthesize this new model just so I can annotate my data set and train my secondary model it's a pretty rare use case. Typically, it's cheaper and easier for them to just pay someone to annotate it, right? And it's a little more straightforward and it's not as experimental and that kind of thing. So if we can figure out a way where you can have a similar level of global differential privacy like this, actually even it's debatable whether this is global or local. It's probably closer to local. Which doesn't have this core assumption, that would be a pretty big breakthrough, and it would be the kind of thing where that's the form of DP technique that would be general purpose, I think, and I would very much like to see sort of someone push through on that front. But obviously, lots of people are trying, and hopefully we'll have something in the next little while.
Cool. Any pointers or thoughts for folks that want to dig more into this area? Where should they start looking for ways to get up to speed on these 3 pillars or your project?
So I mean the 3 activities that we do in OpenMind hopefully are designed to make that as easy as possible. So we build open source tools, we create learning resources, and we build community through like hackathons and through the Slack channel. So the first thing that I'd recommend is join the Slack team and kind of scroll through the articles people are posting. So you can go to slack.openmind.org. And OpenMind is spelled OPENMINED. Yeah, hop in the general discussion, say hello. And then I just finished writing a 9-length notebook tutorial walking from the very basics of kind of remote execution through federated learning and secure MPC. It'll be extended with differential privacy in a bit. And the real goal of that tutorial series is just to walk someone who just knows, in this case, PyTorch, through in a very hands-on kind of way how these techniques work.
Awesome.
Yeah.
Awesome. Well, Andrew, thanks so much for taking the time to chat with me. It was great to meet you.
Great to meet you too.
All right, everyone, that's our show for today. For more information on Andrew or any of the topics covered in this episode, visit twimlai.com/talk/241. As always, thanks so much for listening, and catch you next time.